Hi friends, this is Dr. G. Srinivasa Gupta, Professor from Department of Mechanical Engineering of VJEC JYOTHI Institute of Engineering and Technology. As a part of Dynamics of Machinery course, today we are going to discuss a concept of logarithmic decrement in mechanical vibrations. We will see what is logarithmic decrement, how it arises, what is that expression we can derive. Already we have seen this mechanical vibrations means oscillatory motion of the body from its equilibrium position. That means some work is done against elastic constraints forces, and the body is trying to restore back to its original position. In that translation, the energy will be continuously transfers from one form to other, kinetic energy to potential energy to kinetic energy. If this motion is vibrations are free, then there is no external resistance to stop this, then the body is continuously oscillate. So the body need to be considered as a model. We need to consider the body has some mass and some stiffness, that is elastic property. Then there will be a oscillatory motion of the body. Okay, the model also we have discussed, a mass attached to the spring. It is exact, the model replicates the vibration aspect of an simple object. So terminology also we have seen. Okay, cycle, one complete oscillation is called cycle. For example, okay, suppose displacement is function of time, we know that. If we see the plot displacement versus time period, suppose this variation for particular type of vibration, suppose this variation is like this, okay, then the amplitude is this one. Okay, so the cycle means it is completes one time period. How much? This is one cycle. Okay, particular time period, its repetition is completes, this is called one cycle. So this will move up and displacement increases, decreases, again coming to reaching zero starting position. So this is one cycle. Similarly, amplitude, the maximum displacement, this one is the maximum. We have notated with the uppercase letter X yesterday, just we have seen in the relation. Time period, time for one cycle. What is the time required for this one cycle? This is time period. Then frequency, number of cycles per second. How many cycles this oscillatory motion has per unit time? Then that is called frequency. Natural frequencies without having any external resistance to stop the motion. If body vibrates, then corresponding frequency is called natural frequency. So frequency is number of cycles per second. You will use the unit H. H is cycles per second. Per unit time, how many cycles? Also, we have seen one case. There are four cases we discussed. That is free vibrations with some damping, and forced vibrations without damping, forced vibration with damping. We have seen all these four cases, how the relation can be developed in our previous lecture. Now I am talking about the free vibrations, the vibration with damped condition. That's why I have shown here mass spring damper. Damper also additional element why vibrations are gradually coming down, disappearing. That case is this what I have drawn already. This is a magnitude of amplitude. This is a displacement function of x, and this is time period. Then magnitude gradually each cycle it is going to decrease. Then next cycle decreasing. So goes on decreasing and it will die down amplitude. So this is called because of damping, the displacement or the oscillations are going to be reduced. Gradually it is come down because of damper. A damper having damping coefficient C, and we have seen this relation how we can write using either Newton's second law, Newton's law, or D'Alembert's principle or energy concept. We can write this relation, equation of motion in this case, a damper also there, spring as well as this is the spring and a damper which is also there. Okay, so then these are attached to a mass. In fact, the actual real object is having mass and some characteristics of elastic like spring and some resistance actional, that is called damper. Damping coefficient C, spring stiffness K. These are properties of that object that is having some mass. Okay, for this we have seen the relation. Equation of motion is mx double dot that plus c into x dot, which represents x dot velocity correspond to displacement x, kx. This is the relation. So standard form we can write this by dividing with m each term, then x double dot, and if we write some form 2 zeta omega n x dot plus omega n square x, the meaning of omega n as usually you know that root k by m, and zeta is damping ratio. Damping ratio, you have seen that damping ratio can be written as c by 2 square root of km. Okay, this 2 square root of km we are defining as critical damping. Critical damping means the damping where which is oscillations are that is frequency, natural frequency of the system is going to be coincide with this oscillatory frequency, that is the force frequency or oscillatory frequency. Okay, that is critical damping. Okay, in that case we will write this one relation. Anyhow, so we will see further as what is logarithmic decrement. In case of underdamped system, this zeta damping ratio is c by 2 root km, what we have written is becoming less than 1. Then this is called underdamped. In that case only the damping is gradually down, displacement is going to be down, and gradually it is going to disappear because of damping effect. So this case we are going to take, and in this case only we are defining this logarithmic decrement. So how we know that under damped condition the solution is in the form, because this is second order differential equation, linear differential second order linear differential equation, x double dot do zeta omega n x dot plus omega n square x. This is linear in x second order differential equation. The solution based on the mathematics fundamentals, one can have this is the solution. X displacement is equal to e power minus zeta omega n t into a cos omega dt plus b sin omega dt, where omega d damping frequency it is called, that is omega n into square root of 1 minus zeta square. Actually that is, in this case, that is the definitions. Displacement relation in this form and damping frequency is okay, natural frequency times square root of 1 minus zeta damping ratio square. Okay, this is the relation. In this case we will go further and we will see what is logarithmic decrement. There is a term which is very important. It is logarithmic decrement is the measure of rate of decay of amplitude in an underdamped system. Zeta is less than 1. Here the definition is delta is equal to natural logarithm of x1 by x2. x1 is displacement in first cycle, and x2 is displacement in second cycle. The logarithmic of ratio of displacements in consequent cycles, that is called logarithmic decrement delta. So this damped vibration we have seen, this is the equation. Then the solution is in the form displacement equal to a e power minus j omega nt into sin omega dt plus pi. We have seen this is the general solution in this case. Okay, so then if phi is phase angle is there, then we can write like this. Okay, then omega d is the as usual definition. So amplitude is not constant, it is continuously varying till it decays. Okay, so the envelope a power minus zeta omega n t is called envelope. This is if you observe these terms, what happened? This is the continuously e power minus means exponentially it is decaying the amplitude. Okay, we will see further. Consider suppose successive peaks. This is, let us say here, this is x1, x1. This is, okay, second one, x2. Successive peaks means this is one cycle x1, this is, okay, next one x2, gradually decreasing x2, like that, x3, like that, of course up to xn, let us say. Initially it is, if you use whatever notation, x1 or x0, x1, x2, like that also. Okay, so then if you go for that relation, then you can see that, okay, this x1 we can write, because it is amplitude, ae power minus zeta omega and t. This term represents amplitude at any time period. We are taking t1 time, let us say t time. Then second one, okay, t plus td. Td means because it is damping, this we are writing td. Second one, okay, here this is a time period, how much it is taking. This is td we are writing. Okay, this is t, where as per this equation, this is t. T period it is small t, it is, okay. Then this is t plus td, additional time, that is we are writing. Okay, this period till the maximum amplitude is x2, that maximum amplitude we can write using this relation. That is, are able to understand, I think. So x1 is ae power minus zeta omega and t. X2 is a time of t plus td, as just I mentioned, x2 ae power minus zeta omega and t plus td. Then ratio if you write x1 by x2, then obviously you have seen ae power minus j omega n t. This is x1, and this is amplitude maximum at that time period. So ae power minus j omega n, time is t plus td here. Okay, okay. So then we know that this ratio is going to give e power j, okay, omega n td. It is giving this one, because if you write exponential form, this e power minus zeta omega n t into e power minus zeta omega n td, as you know that. So this is in the denominator you are getting. So if you write, it is positive, j omega n td. This is x1 by x2. Then further if you move and write this ratio, what is x1 by x2? If you say x1 by x2 is this one, and if you write logarithm of log of x1 by x2, if you write natural logarithm of x1 by x2, then obviously it becomes j omega n td. Okay, so this is quite clear. Then okay, so, here because this is delta, this is delta, this is called logarithmic decrement, log of ratio of subsequent amplitudes. Okay, that is a difference of time per j omega and td you got. So then here, okay, if you say j omega and td you can omega n, okay, you can define as td is, you can write td. What is td? Here td is 2 pi by omega d. Let us say omega d damping frequency. Then you can write like this. Then if you substitute this one td in this relation, td is 2 pi by omega d, substitute, then you will get j omega n delta equal to j omega n, td is 2 pi by omega d. So overall you will get 2 pi j omega n by omega d. This you are going to get the relation. But you have seen the relation while we are taking displacement solution and substituting, and there will be a, we can see the relation between omega d and omega n. That is omega d equal to omega n times square root of 1 minus j square. This is the omega d and omega n relation. Okay, in the solution itself, you are simplifying writing this one, this solution form. This is ae power x, displacement at any time equal to ae power minus j omega n t sine omega d t plus pi. Here omega d is omega n into 1 minus square root of 1 minus j square. That we are using here. Then you can write this is equal to 2 pi j omega n by omega n square root of 1 minus j square. So simplified form, it is giving delta equal to 2 pi j by square root of 1 minus j square. Okay, I think you are able to understand this. So that is delta form. So we know that for n cycles, if you write amplitudes starting with xj, x naught and xn is after n cycles, then you can write delta is equal to log x naught by xn. So okay, so you are able to understand, I think, this one. Then final formula of the logarithmic decrement delta equal to log x1 by x2 equal to 2 pi j by square root of 1 minus j square. So in this damping ratio j is less than 1, we said. If it is very small compared to 1, then this becomes equal to j square becomes equal to very small. Then under square root of 1 minus j square, we can j square term can neglect. Then you will get 2 pi j. Okay, in case if damping ratio is very too small, then you can write that one. Okay, so I think you are able to understand this relation. With this, I am concluding this lecture here. Basically, this damping ratio is basically represents the decay of the damping amplitude from cycle to cycle. That is this relation. It is very important relation which is useful for analyzing the vibrations under free vibrations under damping condition. So with this, I am concluding this lecture here. We will meet again in our next lecture.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.